No, not in this class. All right. Mostly because Geiger counters are more expensive than I want to pay money for. All right, whatever. All right, it's actually not that bad. All right, welcome to chemistry. Let's go ahead and get started. We're on page 196 of your supplement, page, I just said it, 303 of your textbook, page 303 of your textbook, page 196 of your supplement. Siri, no one was talking to you.
Exactly.
All right, anyway, that happens way too often. All right, the discovery, let me try that again. The discovery of bombardment reactions in the 1920s and 1930s led to the discovery of many new nuclides. In the mid-1930s, Enrico Fermi speculated that bombarding uranium, element 92, with neutrons might form new elements with higher atomic numbers that did not exist in nature. However, when scientists actually tried such experiments, they were puzzled by the results. Where's my cursor? There we go. Are we really going to do this, Mac? Why? Okay. I have somewhere I'm going with this. Give me a second. Totally love trying to do this right now. Credit. Which one is this? It's going to be this one. I downloaded the videos ahead of time because I'm smart. All right. So when I'm sorry, what? What was that? What was that over there? All right. However, when scientists actually tried such experiments, they were puzzled by the results. Did y'all hear that, or was that just me?
What?
Yeah, okay, cool. It's been a weird morning, so, I don't know. All right, let me see here. What was I doing? Their samples inexplicably kept becoming contained with the common element barium, element 56, despite all efforts to keep the samples pure. In addition, the barium inexplicably seemed to be radioactive. It was not until 1938 that the brilliant Austrian scientist Lise Meitner, along with her nephew Otto Frisch, realized what was happening. They determined, based on experiments by the German chemist Otto Hahn, that the barium was not a contaminant at all, rather than a new type of nuclear reaction was occurring, in which uranium atom was splitting into smaller ones, one of which was barium. They named the splitting process nuclear fission and correctly deduced that the other fission product must be krypton. They also calculated that this fission must liberate a tremendous amount of energy, about 180 to 200 mega electron volts per atom, more than 5 million times the energy released by detonating a molecule of TNT, which is a lot. Okay? In case you missed that, basically what they did is they fired a neutron at it, trying to make a heavier element. Okay? And, oh, whoops, nope, two smaller ones happened because, nope, that's not stable. And actually, it will keep going. Okay? Which we'll talk about here in a minute. A wide variety of nuclides are suitable for nuclear fission. The most important naturally occurring fissionable material is U-235, which comprises about 0.72% of naturally occurring uranium. Again, most uranium is uranium-238, which is not quickly fissionable. That's the way I'm going to word that. Okay, it's fissionable. It's just not going to happen anytime in your lifetime. Okay. A nucleus of 235U can capture a neutron to form an unstable 236 nucleus, which immediately breaks apart into a variety of smaller fragments, namely. Can you work? Thank you. Let me see here. Namely, we have barium, krypton, and neutrons, or barium and, oh goodness, what is PM? Is PM plutonium? I dropped my periodic table. Where did it go? Oh, it's over here.
Almost got it. Any second I'll find it.
Right? Promethium, my bad. Promethium. Because why wouldn't it be? All right. Thank you. You're helpful. All right. Anyway. Oh, yeah. I started searching the periodic table for like the element, and I forget the atomic numbers on screen. I can just... Right? Anyway, I'm not alone. Okay, cool. So anyway, we'll get some neutrons and possibly electrons and gamma radiation out of it. Though more than 200 nuclides of 35 different elements have been found in the products of U-235 fission, the most important feature of these reactions is the production of more neutrons than are used. On average, 2.5 neutrons, I don't know how you get half a neutron, but you know what, averages, are produced by the fission of one 235U nucleus, which in turn can cause other nuclei to fission, therefore producing more neutrons, which can cause other nuclei to fission, and so on. As long as U-235 nuclei are present, such a chain reaction may occur. Maybe, if I can get the slide to come up. Thank you. All right. If a sufficient amount and density of U-235 is present, the critical mass, the chain reaction will be self-sustaining. Okay, and essentially something like this happens. You know, it'd be great is if you went to the correct screen. Okay. So basically, what happens is this uranium breaks apart. I love that. I love that animation. Why are you on 2x? Why? Why?
Wow.
Okay, let's try that again. No wonder it went by so quick. All right. So what happens is a neutron hits a uranium-235, which then sends more neutrons out, which hits more uranium-235, which then sends out more and more and more. And you see how quickly this can escalate out of control, making the substance very hot. As a matter of fact, if it happens quickly enough, the results are rather explosive. Had to do it at least once. All right, but this heat is actually what also makes it useful for power generation, as long as we can control the heat and keep it from, you know, being explosive. It's actually easier than it sounds. We'll talk about that in a minute. Yes, again, much easier than it sounds. It's actually really hard to get it to be explosive. And not hard to get it to be explosive, it's hard to refine it to where it will become explosive. That's the way I want to word that. And in other words, each fission will cause at least one additional fission so that enough neutrons will be released to keep the reaction going. In an abundantly supercritical mass of highly purified U-235, each fission may cause as many as 2 or 3 additional fissions almost instantly. Under these conditions, the chain reaction can proceed so rapidly that most of the U-235 in the sample undergoes fission within a few millionths of a second, releasing a tremendous amount of energy in a nuclear explosion. Intense heat, X-rays, neutrons, and radioactive fission products are produced. Word of the discovery of fission and its implications for a world heading for war quickly reached the attention of a group of refugee scientists in America. Included in this group were Edward Teller, Victor Weisskopf, and Enrico Fermi. Under the direction of General Leslie Groves, oh goodness, that guy must have had the rough time in his early days as a military man, but moving on, and Dr. J. Robert Oppenheimer, these and other scientists worked on producing the world's first nuclear weapon. Just before dawn on July 16, 1945, the first nuclear fission bomb, nicknamed Gadget, was exploded over the New Mexico desert near Los Alamos, releasing energy of approximately 20,000 tons of TNT from the fission of plutonium-239. Basically what happens is they had shaped charges on the outside that force an explosion inward to compress everything and cause fission to be extremely rapid and extremely destructive. A second bomb containing highly purified uranium-235 was dropped on Hiroshima, Japan on August 6th, about a month or less than a month later, 1945, devastating much of the city. On August 14th, 1945, 5 days after a third bomb was exploded after Nagasaki, Japan surrendered, thereby ending World War II. Although the Hiroshima bomb used U-235, the Nagasaki bomb and nearly all modern nuclear weapons use an isotope of plutonium, specifically plutonium-239, rather than uranium. Now, I can't talk about this without talking about the ethics of using nuclear weapons and their consequences. It's just not possible, okay? I'm not going to go too deeply into it, only because time, mostly. But there's argument on both sides of this thing, okay? There's the argument of... let's go back to this time period and try to put ourselves in the mindset here, okay? Yes, America was extremely racist toward Asians at the time, mainly because Japan was one of its enemies, so it was a really easy way for that to happen, much like we just saw with COVID. People were insisting on referring it to as the Chinese virus, and that kind of thing. So, moving on. Anyway, so people's reactions are still going to be the same. What are you going to do? It doesn't make it right, to be clear, but that's just the reality of it. So let's put ourselves back in the mindset a little bit, not too much, of the 1940s. We're in the middle of World War II. There we go. I'll eventually get the sentence out. Okay, and we get word that Germany has discovered fission, and that they're working on it. We know this because some of the scientists have defected to our side who were in the project. Okay? So now, as a military, your job is to get these scientists to get a working weapon using this new technology because it's so destructive. What in the world? Because it's so destructive and so annihilating that if you don't have one, you're basically as good as dead. Okay? This was the idea. Fast forward a few years, the Manhattan Project is getting closer and closer and closer. You guys, when we first talked about, or opened the chapter, we talked about how the first reactor was actually under the stands of Chicago Stadium. Or not Chicago Stadium specific, but one of the stadiums in Chicago. The reason that was done there and then and so rushed with almost zero protection was because that was the kind of time crunch we were on. We thought Germany was close. Like very close. As in scarily close. As in, we might be annihilated if Germany gets this weapon. So yeah, a lot of the protections, a lot of the standard safety procedures for testing something like this went out the window. And that's why that started there, because the thing was to prove the theory first. Fast forward another couple years. Actually, I really need to go into... Where's that binder? Because I feel like I'm leaving a lot out. Is it this one? Yes. Told you guys. All right, I'm going to go into more of this later. But I'm just going to continue giving the summary because I can't find exactly what I'm looking for right this second. And nope. Yeah, I'm going to have to look at this more and find what I'm looking for later. But just fast forward a couple years. I'm going to just kind of give you guys a summary today. Fast forward a couple of years, and Germany is done. Hitler commits suicide. We won that part of the war. Victory in Europe Day. Troops don't get much time to celebrate, though, because they basically pack up and head over to Japan because we're still fighting that war. And so we start really intensely fighting Japan. Up until this point, it was just kind of holding them at bay because we were trying to win the war in Europe first, because that was the more, what we thought, time-sensitive one. Because we thought they were real close to fission. Turns out, not even a little. Like, they had gotten as far as the scientists had told us, and then the project kind of halted. We don't know why. Or at least I don't. Okay? So, yeah, turns out really weren't as in big a danger as we thought. But, the project is well underway, and we're actually pretty close by this point. Well, as we're fighting Japan more and more, it becomes really, really, really evident that they are going to fight down to the last man if we let them, which is going to cost us hundreds of thousands of casualties on our side of the war. And then the first nuke is tested. And it works. And it's devastating. It brings a whole new meaning to the words shock and awe. Now imagine you're the President of the United States. You have this brand new weapon and you have an enemy that's so religiously following their leader that you're going to have to fight them down to the last man, even with Russia's help, and they're going to declare war on Japan. You know this. Even with that, this is going to be a years-long war. We will eventually win. We just have the manpower. But we will lose so many lives in the process. Now consider you also know this as president. Okay, I suppose I can get off the slide so people can just see me. Now suppose you also know this as president. There's no separation between the military and civilians in Japan. None. Here's what I mean by that. Civilians were being drafted not just for war, but to create munitions, to create ammo, to pack together rations. The idea of only targeting a military base is impossible because they're storing stuff in people's homes. Because the people of Japan are being so, again, near religiously following their emperor, that they are doing everything they can to make sure Japan wins. And that's what you're up against. And you know your military just tested a bomb with the capacity to destroy an entire city. So as president, you look at this and you look at the numbers. And as much as it seems a horrifying thing to do, you make a decision. Whether or not it's justified will be argued for the next century. We could still argue it in here. Because hindsight is 2020. Okay, I know it's 2021, so that joke doesn't work. But you know what? Whatever. Hindsight is 2020. We can go back and criticize and critique and everything else. You're not there. So we can argue the ethics all day long. You're not there. You haven't just been fighting a war for the last 3 years that Americans didn't want to get involved in the first place. Because our attitude with World War II was literally, that's Europe's problem, let them deal with it. Until Japan dragged us into the war kicking and screaming. Quite literally. Okay, they had the audacity to bomb us on a Sunday. Okay, that was like part of the thing. Like that was a big deal. The military even took Sundays off back then. Yeah. Okay. So he gets this. Basically decides here's what we're going to do, and him and the military in general. This is a group decision, to be clear. And basically, they decide they're going to go ahead and use the nukes, but they're going to give people a warning. Unfortunately, propaganda is extremely common, so it gets viewed by the Japanese public as nothing more than propaganda. But they drop leaflets with the names of several major cities and says that if you live in any major city, not just the ones on this list, but these are the ones that we intend to potentially target with this new weapon, you may want to evacuate. I mean, who else tells people a list of places they're going to strike? Now, to be clear, the first place they struck was actually not on the list. But the reason why that one was chosen, first of all, in the list, it did say, or another major metropolitan area. Okay, so there was a wild card in there. But the reason that one was chosen was due to weather conditions. It was the one we could see. Keep in mind, you didn't have precise targeting. GPS wasn't invented yet. Literally, their plan was they had to release it while flying over a mile up in the atmosphere in order to give the jet enough time to get out of the way. Okay, they had to drop it from over a mile up. And they do it. They drop the first one. Entire city leveled. People with radiation burns who weren't close enough to actually be taken out, but close enough where they're going to die within the next few days. And it completely destroys the morale of Japan. And the U.S. tells Japan, you have two choices: surrender or we do it again. And the Japanese emperor gets out and holds a press conference and says, "We will not be bullied by American politics. We will never surrender." It wasn't just, oh, we dropped 2 bombs and leveled 2 cities all at once. Nope. So we send a second. And basically the military tells the people making the bombs, keep them coming. Because they're not going to surrender. That's the idea. It's not something that was wanting to be done. It was something that it's the only way we walk out of this with even a fraction of our population left. And I say us and our because I am an American. We are Americans in here. Like it or not, this is part of our history. To this day, we are still the only nation that has ever used nuclear weapons on another nation. Ever. We can argue the necessity of it. We can argue the politics of it. We can argue the morality of it. The reality is it happened. We can't change that. And as barbaric of a device as this thing is, hopefully you also can see kind of where they were coming from. I'm going to go into more details about the Manhattan Project and things. Honestly, your test will probably be postponed because this is where I tend to park this chapter, and I kind of forgot about that. But for right, I'll announce dates later once I've had more of a chance to look that over again because I don't remember where anything is in there. I know it's organized, I just don't remember how. So let's go into talking about nuclear power. So basically, after the war, there's a whole level of secrecy, and actually there's a couple of videos we might show on it. Like, I seriously have a lot of material on this. But after the war, we had this new technology. The only way we knew how to use it so far was to blow things up. Okay, which outside of wartime, not really helpful. So, what we as a country decided to do was try to find a way to use the atomic era to kind of launch us forward as a technology, create jobs, because now you have all these people who were just, the most training they have is, how do you hold a rifle, who suddenly need to enter your workforce. And so a lot of construction projects, hey, great idea. So this was kind of the idea, was to keep the economy going. So over time, we finally figured out how to sustain and contain a nuclear reaction. And so that's what we're going to talk about now is nuclear reactors. I will come back and continue talking about the bombs and things like that. And as far as the Manhattan Project, I just don't want to keep going off the cuff like this because that much I remember off the top of my head. I want to make sure I get all the details right for what else I'm going to talk about. So we're going to go ahead and move forward. A nuclear reactor. A nuclear reactor is any device for safely initiating and controlling a fission chain reaction to produce electricity. They are most famously known for their shape of the cooling tower. That cooling tower has zero radiation coming out of it, has zero radiation inside it. That cooling tower is entirely to allow steam to evaporate off the steam cycle, basically, to cool the steam, hence the name. So that way it can go back in the loop, be heated up, and continue moving a turbine. Okay, that's the idea. If you look at this here, there are actually 3 loops inside a nuclear reactor. Okay, the first loop is inside the containment building, inside the nuclear reactor. This is water that's being used to cool the reactor and output the heat. Okay, so that's the idea here. Let me see if I can zoom in here. I know there's a way to do it. Okay. Let me try zooming in one more time, see if that will... There we go. All right, so right here is our primary loop. Now, this water never leaves the containment building. This loop is kept kind of small because without this loop, the reactor can potentially go into what we call a meltdown. We'll talk about that more later, okay? So this water is more important than just expelling heat. It's also keeping the thing cool enough so that the uranium itself doesn't actually melt, okay? That's the idea. Okay, so that goes into a steam generator or a boiler. That energy gets transferred to different water, okay, which is run through electrical generators because it's through steam. So it's basically steam powered, but without burning the coal. Does that make sense? And we'll talk more about why that's a critical feature in a little bit, because we're going to compare and contrast the different types of energy production. Okay, and if you actually look at the data, nuclear power is by far the cleanest, most efficient way we have to generate electricity to this day. I am including solar panels and wind power in there. We'll talk about why. Okay, I promise we'll get to that discussion. That's not a blanket statement that I don't have facts for. Okay, I'm not trying to indoctrinate. I am pro-nuclear. Just to be clear, just to throw that flag right out there, I understand. However, it's because of the data, not because I just think splitting atoms is kind of cool. All right? I promise. I will get to that discussion. There's so many discussions to have in this chapter that just, oh goodness, we don't have time for. All right, so we're going to generate that electricity, and then what happens is it goes through a condenser, much like the condenser in, this is oversimplified, much like the condenser you have in your air conditioning unit. Okay? Similar-ish. So that allows it to condense and continue its loop. Well, that condenser has to take the heat somewhere, and that set of water, that tertiary loop, is taken and evaporated off to release the heat safely into the environment that didn't make it into electricity. So you'll notice this is separated by 2 layers of separation, so there's no possible way for that steam to become radioactive. Does that make sense? Okay, that's the key thing I want you guys to take away from this diagram. We're not straight up evaporating the water that was in contact with the nuclear product, because then you could get radioactive steam, and that would be a problem. Okay, to be clear, we know that. It's fine. That's a self-contained loop. That gets transferred over for the generation. Technically, that water would probably be fine, but for the interest of being really careful and being extra sure, we separate it out again. Okay, does that make sense? You all follow me? Basically, we have to liquid cool it. Okay, that's what we're doing. Yep, basically. All right. So that is a nuclear reactor in a nutshell. We have to, in order to be able to use any form of nuclear, well, you know what, let me just get into the book. With the end of World War II, the use of nuclear fission for electrical power production rather than destruction was pursued. Honestly, it would have probably been pursued first because it's easier to refine the material that far. But again, we were on a time crunch. Oh, you know what, I should probably be showing the slides again. Great. That means I didn't show the diagram on stream. Nah. All right, that previous diagram was on page 305 for distance learners. But with the end of World War II, we went to this. If a mass of uranium is not highly purified, U-235, an atomic explosion cannot occur, even if a critical mass is present, because a more common isotope, U-238, slows down the reaction too much. Okay, unless U-235 is nearly the only thing there, it cannot create a nuclear explosion. Not is, well, probably not, as in cannot, as in unable to can. Okay? As in it is impossible. That's a very key thing because we're going to talk about that. Okay? Instead, a more gradual chain reaction may result in which large amounts of heat are produced. Under controlled conditions, this heat can be used to produce electricity, much like we just showed. In comparison, the combustion of 1 gram of coal produces about 30 kilojoules, whereas the fission of 1 gram of uranium-235 produces, 80 million kilojoules of energy. 30 versus 80 million. Which one is more? Yeah. We get a whole lot more energy with the same amount of mass going in. Yes? I can't hear you. Huh? What? What other one? I'm very confused. Here? Oh, we'll talk more about that. Because it doesn't have time to get completely cool. That's why it's warm. It's still warm from the previous round. It doesn't get completely cooled down. We don't refrigerate it. It's not necessary. We just need to get the heat out fast enough. So warm water can still pick up heat. Anyway, fission of 1 kilogram of 235U produces as much energy as the combustion of 2,700 tons of coal. 2,700 tons versus 1 kilogram. Okay, a lot less uranium is needed to do the same amount of work. without the air pollution problems that must be overcome when burning coal. Again, we'll talk about that. The major difference between coal-fired or oil-fired plants and nuclear power plants is the source of heat for producing steam. In a coal-burning plant, the heat from burning coal is transferred to boilers or steam generators to produce high-temperature steam, which is then fed to steam turbines, which turn large electrical generators to produce electricity. Instead of burning coal, the nuclear plant uses heat using a nuclear reactor, which is that device. The most important part of the nuclear reactor is the fissionable material to produce energy. Most U.S. reactors use uranium dioxide as the primary nuclear fuel. Natural uranium consists of about 99.3% U-238 and 0.7% U-235, but only U-235 is fissionable under the conditions found in a nuclear reactor. Consequently, the uranium is usually processed to increase U-235 to 2 to 4%. You want to write that down somewhere? I didn't put it in your supplement. It's 2 to 4%. That's how far it gets enriched. Normally, it's about 0.7. Okay, we're going to do some quick maths here.
Where am I writing this now?
Somewhere near enrichment. Enrichment. Sorry, I'm having a hard time actually getting words out today. All right, so normally 0.7% 238 uranium. Okay? No, 235. 235 is the fissionable one. I always try to get the numbers mixed up in my head. Be careful of that. Okay. Then, reactors are about 2 to 4% depending on your reactor design. Okay? What this does is it allows it to reach critical mass for a sustained reaction, not a critical mass for an explosion. Here we go. Okay. For a nuke, you need at least 50% 235U. If you want it to be good, you want it to be closer to 90. Do you see the vast difference here? This is incapable of going into a nuclear reaction. Again, it would be hard, it would need ideal conditions. It is physically, scientifically, and literally when I say physically, I mean according to the laws of physics, impossible. Okay? And that is a key thing because one of the biggest hindrances to nuclear power adoption is people are scared that essentially a nuke will go off in their hometown. It can't. It's not that it would be hard. And to be clear, there are dangers, and we're going to talk about that. Okay? I'm not trying to undersell the danger here. But there's dangers of coal burning too. Like, there's dangers of everything. There's dangers of existence. Okay? So we're going to talk about the pros and cons. We're going to get into that, I promise. But the main thing I want you to take away today is that it is impossible for a nuclear reactor to act like a nuke. It can't do that because it's not refined to that level of purity. Even the two worst incidents in nuclear history released far less radiation than a nuke would, did far less damage than a nuke would. All right? And so I want to make that clear. We're going to talk about Chernobyl because, my word, if there was ever a monument to human stupidity, it's that one. Okay? And then Fukushima Daiichi, yes, that one is a more recent one. Yes, that one's a bit more scary. However, okay, also human stupidity. We're going to talk about it. Okay. We will talk about that later, though, because I do not have time today. All right. Other key components of the reactor include the water or graphite moderator, which slows neutrons for easier capture by U-235. The whole point of a control rod is actually not to... the whole point of it is to make it easier for the reaction to occur. It's basically acting as a catalyst. And then you have the coolant, which carries heat out of the core. And then the control rods. I'm sorry, water and moderator are different. Or sorry, moderator and control rods are a different thing. I'm sorry. The moderator basically slows things down enough for the reactions to occur so that the way the neutrons actually have the chance of hitting the nucleus. Okay, that's the idea. The control rods absorb some of the neutrons. I was getting that backward when I was saying it. Sorry. Control rods absorb some of the neutrons. If you put them in all the way, they'll absorb basically all of them and basically shut the reactor completely down. Cool. So that's kind of the basics of the layout of a nuclear power plant. We're going to leave off there, mostly for the sake of the bell rang. So I will see you guys tomorrow. I'm already just going to announce it. Your test is postponed to at least next week. Or, well, it will be next week. I just don't know what day yet. Okay? So your test is postponed. Your Chapter 17 homework will also be postponed until we finish the section. There's going to be a lot of sidebars. So, and by sidebars, I mean like actual education. So, all right, we good? All right. I'll see you guys later.